discussing automation in hematology, automation with respect to hematology. That's what we'll be discussing today. So our outline will be to discuss the whole blood cell analyzer, automated hematology analyzer, which includes the whole blood cell analyzers. Look at the basic principle by which they operate. Look at some of the results output from those machines, and then look at some practical problems, how they help in trying to unravel the clinical condition of a patient. That is the problem solving or troubleshooting with the results from our automated hematology analyzers. So basically, we are concentrating on automated hematology analyzers. So our objectives at the end of this lecture, the students will be able to explain the different principles of automated blood cell counting and analysis, describe how the general principles are implemented on different instruments, identify the parameters directly measured on the 4 analyzers discussed. Okay. Explain the derivative of calculated or indirectly measured parameters for the same 4 analyzers. Okay, I'm taking time to read this so that some of you will still have time to join. Interpret and compare patient data, including white blood cell, red blood cell, and platelet histogram or cytogram or both, obtained from the 4 major hematology instruments. Explain the general principles of automated reticulocyte counting. Identify sources of error in automated cell counting and determine appropriate corrective action. So these are some of the objectives. So what is automated hematology? It's the performance of hematology lab investigation by using an automated analyzer as opposed to manual procedures. There are various hematology analyzers depending on operating principles and the parameters they analyze. Why do we go for automation in hematology, especially in full blood counts? What is the advantage of automated analyzers in hematology? We say that they significantly increase the number of patients to be analyzed, making more efficient use of laboratory resources. They give an estimate of many variables which are manually not possible and produce data with increased reliability, precision, and accuracy. The automation in hematology is efficient, lacks inter-observer variability, and size distribution errors. Data can be stored in automated analyzers. They analyze and produce results within a very short time. So we choose automation in hematology, especially in full blood counts, because the process is more accurate, less time consuming, and also produces a number of parameters which manually will not be achievable. They help to evaluate symptoms such as weakness, fatigue, bruising, that is the output of the result from full blood count. They help to evaluate symptoms of weakness. Somebody that is complaining of weakness and you were able to carry out the full blood count and observe that the hemoglobin level is low, that may be contributing to the weakness. Fatigue, bruising, fever, or weight loss. When somebody have fever, you expect the WBC to be high. Okay. To diagnose conditions of anemia, infection, to diagnose disease of the blood like leukemia, to monitor the response to some types of drug or radiation treatment. So these are some of the advantages of automation in hematology. What do automated analyzers perform? Automated analyzers, what do? They count WBC. red blood cells and platelets. They measure hemoglobin. They calculate hematological indices. The absolute values. Okay. Some can perform differential three parts differentiation of five parts differentiation. Some can also indicate abnormalities of red blood cell, platelets, and WBC. We will see all that. So complete blood counts perform on automated analyzers. We use EDTA blood that is well mixed. Okay. The complete blood count, some in places they refer to it as complete blood counts. In some locations they refer to it as full blood counts. All of them mean the same thing. So the sample that is used for this analysis is the well mixed EDTA sample, the preferred sample choice. Complete blood count is a group of tests giving results of the blood parameters, the blood cells in the body. It counts the blood cells, counts the white cells, counts the red cells, counts the platelets, and also their indices, some other calculations from those parameters. It also gives their results. Okay, the tests are simultaneously done in less than a minute. It has produced all these results that can take a whole almost 4 hours before a scientist will be able to achieve the same feat manually. When the performance limits of an automated hematology analyzer are exceeded, a manual method of cell counting and blood smear review must occur. This is trying to state in situation where a hematology analyzer, instead of really characterizing the cell type in the blood or in the sample, it flags it produces some results. They will call it flag. It will flag WBC, flag lymphocyte, or flag platelets without actually characterizing the cells very well to know exactly what population is there. So in such situation, we advise to now do the film and then look at the morphology of the cell to be able to say accurately what exactly is happening. So what this statement in essence is trying to let us know is that you can't actually, even as we automate and we advance, we can't rule out completely the principle of blood film making and reading of blood film. So that is why you must not, as a hematology, you must be able to make your blood film, identify blood cells, because when the chips are down, you still go to make your blood film to be able to know what the machine is flagging. Okay, sometimes. So for our manual counts, when you look at this slide, you can see what we use to, before you can do a complete blood count. Some parameters do not as fully as the automated analyzer can give. You find out that these are the instruments we need. We need the Nuba counting chamber that is ruled like this. We need the hemocytometer, okay, for calculating our PCV. We also do our platelets, we do the ESR, and we count with this counting machine, and then check the results with the microscope, which is very, very time consuming. Before you can finish a patient sample, you may be spending up to hours. Okay. So you can see the a Dutch scientist who is a businessman and a scientist. Okay, he is commonly known as the father of microbiology and one of the first microscopists and microbiologists. Van Leeuwenhoek is best known for his pioneering work in microscopy and for his contribution towards the establishment of microbiology as a scientific discipline. So he started observing microorganisms under the microscope, introducing the scientific world into the technology of microscopy. So with that, in the manual procedure, this is what will be obtainable, as you can see in this video. Okay. So to use the Nuba counting chamber, okay, you can see the blood cells, how they appear in the film. You can see the manual method, using microscope. Okay. This is just for one patient you are counting, or you can put two if you're an expert. Sorry. And then white blood cells, okay, small squares, to count erythrocytes. Okay, this is the process itself for the manual counting. Just to count erythrocytes. Gently mix to avoid lysing the cells you want to count. You have to have patience. charging the chamber. As you're doing it, you also avoid forming bubbles. Okay, you can see the view under the microscope for counting red blood cells. And see the squares. This is for white blood cells. It counts around here. Okay. The cells that fall within this margin are not counted. So after that, you do your calculations. Okay. That's calculation also done manually. All this whole process, the automated machine can produce results, all the results in less than 1 minute. Of course, in the manual process, you should know that you count the white cell, which has different um, dilution fluid, or from the red cell, which has different dilution fluid, and also platelets. If you want to count platelets, the same process, different dilution fluids. Okay, so you prepare each of them individually and repeat the counting in a different way individually, just for one patient. So it is quite time consuming. As you've seen for, the erythrocytes. Okay, so because of the large volume of labor involved in manual process of blood cell counting, the process of automation was quickly developed, came into play, and since its development, there have been modifications, okay, improvements on what was earlier developed in the early days when it was introduced. So when you look at these slides, you see some of automated hematology whole blood analyzers. Looking at this slide, you can see some of the instruments, some of various designs from various companies, all of them having different capacities. Some we call them 3-part hematology differential count. Some we call 5 parts hematology differential count. The 3 parts can differentiate is the white cells into 3 population. Okay, it differentiate the neutrophils and then the lymphocytes, and then others it classifies them as mid. So we refer to that as 3 parts differentiation. They differentiate the white blood cells into 3 population, while the 5 parts differential differentiates the 5 parts of the white blood cell: neutrophil, lymphocyte, monocyte, basophil, eosinophils. It's able to characterize all of them and identify them. That's what gave it the name 5 parts. When you look at this diagram, it's showing us the output, the result output from an automated analyzer. You can see the whole process that is taken manually to count for WBC or red blood cell, the whole process that is taking us hours. With an automated machine, in less than a minute, we have produce a whole lot of parameters from the white blood cell, which has clinical significance to the clinical presentation of any patient. So what are the advantage and disadvantage of automation? Automation is very good because of the speed with efficient handling of, okay, of a large number. Sorry, this is a large number of samples. Okay, large number of samples can be handled. It is accurate and precision quantitative blood test. Okay, it's accurate, it's more accurate than human error. You can see, looking under the microscope and counting the cells with your eyes, counting it, you find out that definitely you must miss one. Okay, if you want to try it, let one person count a sample for white blood cell and another person give another person the same sample to count at the same time, maybe in different lab. You find that they can never come with the same results. They may be too far apart depending on the human errors that were introduced. Ability to perform multiple tests on a single platform. Multiple tests, it's counting WBC, it's counting platelets, it's doing hemoglobin analysis and all that. Okay, significant reduction of labor requirements, because in those days when you go for posting, those days they don't use automated hematology analyzers. When you come to hematology lab in those days, you find out that one person his duty is just counting platelets, the other person is just counting WBC total, that is the total count. Then another person is doing the film, is reading the film. Okay, so the work is not really one person doing it, so you can imagine. So with the introduction of automated hematology analyzer, there is significant reduction in labor requirement. A lot of persons are not required to count white cells. So what are the disadvantages of automated hematology analyzers? Flagging of a laboratory test results demand laborious, intensive manual examination of a blood smear film. Okay, when you are counting the red blood cells, sometimes the machine flag. Okay, they flag, and when they flag a particular subset of cell like this, because they were not able to characterize the cell perfectly, so the scientists will now start the work of going back to the manual process to do the film, and then be able to identify those cells that the machine were classifying as flags, that were flagging. Comments on red blood cell morphology cannot be generated sometimes, but with new advanced technology, sometimes some of them have been able to produce some level of comments. Platelet clumps are counted as single, giving a false reduced count. Yeah. Erroneously increase or decrease result due to interfering factors. It is expensive with high running costs. Okay, because of the reagents that are involved in the automated hematology analyzer, sometimes the price can be as expensive as 5,000 naira. So it's quite expensive. So the discovery of automated hematology analyzer, the development follows the discovery of microscopy. Okay, in 1852. These are the historical landmarks in the development of automated hematology analyzers. We have light scatter and absorption measured by eye, okay, with the eyes. So there's a whole lot of improvements on the machine that were invented, with subsequent improvement on technology and accuracy and precision to count more cells. That's the historical development. Still have a long way to go, so we may have to be fast. So types of automated hematology analyzers based on WBC differential, I've said that earlier, because we classified the automated analyzers based on how they were able to characterize the subpopulation of white blood cells. We have three parts differential. We said it differentiates the granulocyte, the lymphocyte, and now classify others, the monocyte, the basophil, the eosinophil. It packs them together and say that they are mid, okay, mid cells. Then the 5-part hematology differential analyzer will be able to characterize the neutrophil, tell you that neutrophil is 6, eosinophil is this, basophil is this number, lymphocyte is this number, monocyte. So it's able to identify and characterize these 5 white blood cells and also count them. Then we have another 7-part analyzer. In addition to counting differentiating the white blood cell, they can also identify nucleated red cells and also abnormal or atypical cells and immature cells. Those are advanced one, but they are available. So there are some basic technology that are involved in these machines used to be able to count the cells in the body, or cell counting and sizing for WBC, red blood cell, and platelets. Some of these machines use what we call electrical impedance method, radio frequency, optical scatter, with or without cytochemistry. Then for analysis of hemoglobin, the spectrometric method, they use Cymet hemoglobin, cyanide-free hemoglobin. So you are going to look at these basic technology for counting the blood cells and how the principles behind each. So the counting of the cellular elements of the blood, the erythrocytes, the leukocyte, and the platelet can be based on the following methods. Can be based on electrical impedance or optical scatter or radio frequency. These are the principles behind the process by which these analyzers identify the blood cells. So looking at the electrical impedance process, the impedance principle of cell counting is actually based on the detection and measurement of changes. Okay, it detects and measures changes in electrical resistance produced by cells as they transverse a small aperture. Okay, you can see Coulter was the one that developed this principle of impedance, and it's called the Coulter-Wallis-Coulter principle. It's called the Coulter principle. Okay, with his younger brother, that was their history, how they formed the company and all that. Okay, so but the principle of the uh, electrical impedance is that it counts cells based on the detection of the impedance. Okay, it counts cells based on detection and measurement of changes in electrical resistance produced as cells by cells as they transverse a small aperture. When you look at this diagram, okay, as the cells suspended in this fluid move past this small aperture, the impedance, the resistance that is being generated as the cell moves across this aperture is what the Coulter principle, the impedance principle, uses to count the number of cells in a suspension, okay. So the electrical impedance or voltage direct current resistance is the Coulter principle, was the first principle developed in automated hematology analyzer. Okay, you can see that a stream of cells is in suspension. A stream of cells in this suspension, the diluents, okay, passes through a small aperture. This is the aperture here, across which an electrical current is applied. You can see the electrical current is applied across it. Okay, each cell that passes alters the electrical impedance and can thus be counted and sized. Histogram showing the size distribution of white cells and red cells and platelets can be generated. Sizing is based on impedance technology. So this is how the first developed automated hematology analyzer, which used the principle of impedance developed by Coulter. This is how they were able to count these cells, okay, as they move past the electrical gradients which was produced. And of course, there will be a resistance impedance as they pass, and as that happens, they will pick it as a signal that a cell has passed. Okay, that is the principle of impedance developed by Coulter. So the Coulter principle is based on the fact that the polyconductive blood cells are suspended in a conductive diluent. Okay, the diluent is passed through an electric field created. It's electric field created between two electrodes. The liquid passes through a small aperture. The passage of each particle through the aperture momentarily increases the impedance, that is the resistance of the electrical parts between the electrodes. The increase in impedance creates a pulse that can be measured. The number of pulses is equals to blood count. You see how they arrive at their cell count, okay? The amplitude, that is the height of the pulse, is equals to the volume of the cell. So using these two parameters, they will be able to characterize the cells. Okay. So okay, let's see this the beginning of blood cell counters. What's this? Oh no. What is this? Okay. This video should play. Doesn't want to play. Wow. Okay. Some mixed up here. Okay. So that is the impedance method of blood cell counts. Wanted this video to play. It's like it's not playing. Okay, let's go ahead. This slide, it's misplaced. So we also have a radio frequency. We also have radio frequency, okay, as a principle of operation of some of the automated hematology analyzers. Each hematology analyzer has its principle by which it operates based on the analysis it will be able to perform. So we've seen the impedance principle. We also have the radio frequency principle, okay? The low voltage in radio frequency principle, low voltage direct current impedes, can be used in conjunction with a radio frequency, okay? Low voltage direct current impedance in conjunction with radio frequency resistance or resistance to a high voltage electromagnetic current flowing between both electrodes simultaneously, okay? Although the total volume of the cell is proportional to change in direct current, the cell interior density is proportional to the pulse height or change in the radio frequency signal. So when you look at this diagram now, you can see the radio frequency current in conjunction with the direct current, okay, can be used to differentiate or characterize blood cells. The radio frequency direct current detection method showing simultaneous use of DC and RF in one measurement system as in the 6MEX, okay, this instrument in particular uses radio frequency in combination with direct current, okay, to create electrical gradients that allows it to, apart from sizing the cells, it also goes to analyze the the structure, the internal complex, the complexity of the cytoplasm of the internal structure of the cell to enable it to also characterize, be able to characterize cells further, more than the impedance method. So the high voltage electromagnetic current is used to detect cell size based on the cellular density. The radio frequency pulse, you can see these two combination, you can see the DC signals, okay, you can see the radio frequency signals, okay. The high voltage electromagnetic current is used to detect cell size based on the cellular density. The radio frequency RF pulse is directly proportional to the nuclear size and density of the cell. RF or conductivity is related to the nuclear cytoplasmic ratio density and the cytoplasmic granulation. So in this diagram, which is an illustration of the cell volume measurement with direct current. See, with direct current signal measures the cell volume, voltage changes versus measurement of cell nuclear volume complexity with change in radio frequency. You can see the radio frequency here penetrating through the internal structures of the cell, being able to analyze the nuclear contents of the cell. Okay, the two measurements can be plotted against each other to form a two-dimensional distribution scatter plot. Okay, so radio frequency is an advanced principle of counting blood cells. Okay, I think it's still the same thing. Okay, low voltage DC impedance may be used in conjunction with radio frequency, as we've been saying, resistance or resistance to a high voltage electromagnetic current flowing between both electrodes simultaneously. Although the total volume of cell is proportional, the total volume you can see from the diagram is proportional to the DC change in DC. The cell interior density is proportional to the pulse height or change in the radio frequency signals, as you saw in the diagram. Okay, some of the before we go into optical principle of blood cell count, we also have some instruments, some of the automated machines. We have some of the manufacturers. We have the Coulter instrument, Sysmex instrument, Abbott and Sysmex, Siemens, Abbott, Coulter. These are different manufacturers. Okay, so each of these instruments have the principle they use to identify blood cells. Okay, method for white blood cell differential determination. We have the VCS technology, single channel, that analyzes approximately 8,000 cells. These are principles for this some of these instruments. That is, the VCS technology means volume, conductivity, and scatter. Okay, we'll still look at it. Okay, so when you go into the analysis of how this instrument actually analyzes these cells to bring back, they scatter the cells in various different angles. Okay, and that is what is being depicted here. May not have to bother you with that. Okay, we have peroxidase staining. Some instruments use peroxidase staining to count the cells. Okay, the flow cytometry are also being used, but I want to get to optical method principle for cell analysis. So this is just trying to tell us different instruments and the principles of which they use to count cells. Okay, we have a volume VCS technology, trying to explain the VCS technology as opposed to using light loss to estimate cell size. VCS utilizes the Coulter principle of DC impedance to physically measure the volume that the entire cell displaces in an isotonic diluent. Don't want to bother you with this. Want to get to, okay, optical scatter principle. These are the principles I want to highlight. The principle through which the automated hematology analyzers use to count cells. We talked about the impedance principle. How does it work? We talked about the radio frequency, okay, which uses in combination with DC direct currents to analyze blood cells. These are the major ones. This is what I want you to have in mind now. Then we have another third principle by which this machine can count cells, which we call the optical scatter principle. So the optical scatter principle, so I need to rearrange this slide. The optical scatter principle, excuse me. The optical scatter principle, also known as hydrodynamic focusing, method of cell counting and cell sizing, makes use of laser light. The principle: a diluted blood specimen passes in a steady stream through which a beam of laser light is focused. We will see the diagram. As each cell passes through the sensing zone of the flow cell, it scatters the focus light. Okay, as each cell passes through the sensing zone, just like the aperture in the impedance principle. This one, the cells are passing through the sensing zone where they can be detected. Okay, as each cell passes through the sensing zone of the flow cell, it scatters the focused light. Okay, number of pulses generated is directly proportional to the number of cells passing through the sensing zone in a specific period. Characteristics of light scatter. Optical light scatter, that is, when light is scattered, some at which angle, some are diffracted, some are reflected, all those principles of light are being employed in this process of cell counting too. Okay, so this is engineering. What do we do? Electrical engineering. So those principles of light, when light hits an obstacle, it is either refracted or reflected. All those principles are employed here in sorting out these cell types. So characteristics of light, that is, how are the lights scattered? How does the cell scattered? Are being scattered. You see, the optical light scatter. Light amplification is generated by stimulated emission of radiation. There are three independent processes involved: diffraction and the bending of light around corner with the use of small angles, refraction and the bending of light because a change in speed with the use of intermediate angles. Okay, you see it, the ones that are refracted because of a change in speed, okay, and they happen at intermediate angle. Reflection and light rays turned back by the surface or an obstruction with the use of large angles. So if the light is diffracted, okay, it's stays at the corner with small angles. Okay, so some cells, depending on their size and their internal complexity, can either diffract light, and those cells, they know that they will pack at a small angle of reflection, so they use that angle of diffraction to know that the population of cells here are cells that have the capacity to diffract this light to a small extent, diffraction, or is it refraction, bending with an intermediate angle? Some cells have the capacity to cause the light to be refracted in an intermediate angle, and they will use that characteristics to pick those population of cells that have that capacity. And some cells can cause the light to be reflected in a larger angle. So depending on the angle where which the cells diffract or refract or reflect the light, they will be able to sort out, characterize blood cells. So angles of light scatter, this aids in cellular analysis. These angles of scatter aids in cellular analysis. We have the forward light scatter at 0, diffracted light, which relates to the volume of the cell. Okay, forward low angle light scatter. These are the characteristics of light when it hits an obstacle that they are using to actually characterize the cell. So you can think of it, and even improved if you go into biomedical engineering, this is where you can even put in your expertise as a hematologist and then also be able to advise the engineers on how these cells behave, and they will now know how can they, what technology, how will they be able to identify such things. So that is what happens in some of this engineering development of some of these instruments, so that some of you can actually find yourselves into instrumentation at the end of the day. So forward low angle light scatter relates to the size or volume. So they are using the characteristics of these cells and also based on how they reflect, diffract, or refract light to be able to sort them out. That's basically all this grammar we have been talking since. So forward high angle allows for description of the refractive index of cellular components. Okay, they also go into the internal complexity of the cell. If the cell is heavily granulated, there's a way it will cause the light to bend. If the cell is not the one that is heavily granulated, there's a way, depending on the internal complexity, and this helps them to identify such cells. Orthogonal light scatter at 90 degrees produces data based on reflection and refraction of internal components, which correlates to internal complexity. So this will help them sort out cells into monocytes, depending, you should know. Okay. Optical scatter and or absorption with or without cytochemistry. Okay. This may be used, I think this is exactly what I've been explaining. Okay. This is exactly what I've been explaining earlier. I'm talking about the light source and the properties of lights. Okay. Is there any new thing here now? The laser light, which is termed a monochromatic light because it is emitted at a single wavelength, okay, differs from bright field light in its intensity. Bright field light is the one we use in microscopy. Bright field light. So in this optical system, what they are using is laser light. It's a monochromatic light. Okay. It differs from bright field light in its intensity and coherence. That is, it travels in phase, and low divergence or spread. Okay. These characteristics allow for detecting interference in the laser beam and enable the enumeration and differentiation of cell types. So this is the diagram showing the optical uh, laser. Okay, you can see the system. When you read this right up here, you can find out from here how these cells scatter, this population of cells are scattered, this population of cells. Okay, it also sort out this population of cells, and then you can see at the end of the day how the cells are sorted out, and this population that are here, they pick it up as being a same population of cells and be able to name it. The ones that are being reflected or refracted or at this angle, they also pick it up as different population, and using what do they call it? Using a cytochemistry, some staining, they'll be able to also differentiate. Is cytochemistry, when they add staining, be able to differentiate this population of cells. You can see that these ones that diffracted this are actually the same because they almost stain the same. Okay. So as the cells pass through the sensing zone and interrupt the beam, light is scattered in all directions. Light scatter results from the interaction between the process of absorption, diffraction, okay, diffraction, bending around corners or the surface of a cell in a small angle, just like we said, refraction, bending because of a change in speed in an intermediate angle, if you go back to the other slide, and reflection, backward scatter of rays caused by an obstruction at a wider angle. Okay, the detection of scattered rays and their conversion into electrical signals is accomplished by photo detectors photodiode and photo, all these things are electrical terms, please. Okay. Okay, forward angle light scatter at 0 degrees. Okay. It correlates with cell volume, primarily because of diffraction of light. I know that diffraction of light is at a smaller angle. Orthogonal light scatter at 90 degrees or side scatter results from refraction and reflection of light from larger structures inside the cell and correlates with degree of internal complexity. Forward low angle scatter 2 to 3 degrees and forward high angle scatter 5 to 15 degrees also correlate with cell volume and refractive index or with internal complexity. Differential scatter is the combination of this low angle and high angle forward light scatter. Okay. We also have a flow cytometry is advanced okay. Flow cytometry is defined as the simultaneous measurement of multiple physical characteristics of a single cell. The principle is that a suspension of stain cells using fluorescent dyes is pressurized using gas and transported through plastic tubing to a core slow chamber within the instrument. Forward scatter is proportional to cell size and side scatter proportional to cytoplasmic granularity. Okay. Okay, so in summary, the optical detection principle in the optical or hydrodynamic focusing method of cell counting and cell sizing, laser light is used. A diluted blood specimen passes in a steady stream through which a beam of laser is focused. As each cell passes through the sensing zone of flow cell, it scatters focused light. Okay, it will scatter the focused light. Scattered light is detected by a photodetector and converted to an electrical pulse. Number of pulses generated is directly proportional to the number of cells passing through the sensing zone in a specific time. Okay, so when you look at this diagram, you can see the output of this process, how it's able to analyze the blood cells based on their internal complexity, based on how they refract or reflect or diffract right. You can see here the population, they have a red blood cell ghost. This is where they will stay. Okay, you can see the lymphocytes, how they reflect the light and also pick up the stains. Okay, these are the monocytes, are this population of cells picking up these things. These are the neutrophils, can see they pick up these things. Then these are the eosinophils. Okay, and you know that the eosinophils, the internal complexity, the eosinophils are highly granulated. You see where they are, is it diffracted or what, reflected? See, they are reflected. Okay, this is another diagram depicting this drawing. Okay, so this is how these machines count white blood cell. All these principles we've been talking about, reflection, refraction, diffraction, we are trying to count white blood cell. But the same machines also estimate our hemoglobin using some of these principles. Some of them use the hemoglobin concentration is measured automatically by a modification of the manual assignment hemoglobin method to reduce the toxicity of assignment. Some system replace it with a non-toxic material, sodium lauryl sulfate. So all these ones principle we are talking about are for counting white blood cells. So for the same machines to count our red blood cell, they use the Simon hemoglobin method. Some of them use non-alternative ones that are non-toxic. Okay, the red blood cells are counted automatically by two methods: aperture impedance, where cells are counted as they pass in stream through an aperture, or by light scattering. The precision of electronic counting for red blood cells is much better than the manual count, and it is available in a fraction of a time. This made the use of the red blood cell indices of more clinical relevance. Okay, so for the PCV and red blood cell indices, the pulse height analysis allows either the PCV or MCB to be determined. So the pulse height analysis, they capture in, they incorporate this some statistics to be able to come up with the red cell indices, which you can see in some of the slides that we'll be seeing now, and also the clinical implication. More important is for you to know the clinical implication of any cell is when the white blood cell or neutrophil, taking them individually. What is the clinical implication of a increased neutrophil? What is the clinical implication of a reduced neutrophil? What is the clinical implication of changes in the morphology of the neutrophils? All those things you go to UNTH to learn. This is when you put them in practice. You must know the clinical implications of abnormalities in any cell in the human body. As a hematologist, that is the core, that is your core area. Okay. Some of the hematological indices and how they are being calculated. I won't waste time here. When you look at it, you'll be able to know the formula. Okay. Yeah, I won't go there. We've discussed the white blood cell counts in details. Okay. So for these automated hematology analyzers to count the retics are the immature red blood cells. Okay. An automated retic count can be performed using the fact that various fluorochromes combined with RNA, you know, the RNA, the retics has some RNA in it, unlike the mature red blood cell, which does not have RNA, of the reticulocytes. Okay, so some fluorochrome combined with the RNA of the retics. Okay, fluorescent cells can then be enumerated using a flow cytometer. An automated retic counter also permits the assessment of retic maturity, since the more immature retics have more RNA, fluorescent more strongly than the have more RNA and fluoresce more strongly than the immature retics found normally in peripheral blood. Okay. Another thing that is important, apart from you being able to describe the clinical implication of every abnormality in every cell, okay, you should be able to also be able to describe, evaluate the output from a hematological analyzer, looking at the graph the machine produced, and that will be your assignment. I would give that to your class rep to explain to you very well. That will be our CA. We have to go and get the output of abnormal hematology analyzers, print out, and also describe the findings there. So these hematologic analyzers sometimes use graphic representations of frequencies. Histogram as seen an automated hematology analyzer. General histogram characteristics. The characteristics of this histogram is that graphic representation of cell frequency versus cell size, x-axis in femtoliter. The y-axis are representing the frequency, that is the number. The x-axis are representing the size. They provide information about erythrocyte, leukocytes, and platelet frequency and their distribution about the mean, and also depicts the presence of subpopulations. They provide means of comparing sizes of patient cells with normal population. Shift in one direction or the other can be of diagnostic importance. I know some of you must have come they say left shift or right shift. If you don't know what it is, you go and find out what it means. So normal histogram, okay, the WBC, because each of the cell population have their histogram in the output from the automated hematology analyzer. For the WBC, the normal histogram is being described as trimodal distribution with individual peaks and valleys at specific regions. Okay, trimodal, lymph monocytes, glands. Okay, RBC is described as unimodal, so that if you see, look at the histogram of the printouts and you find out that the WBC histogram is not trimodal, maybe it's pentamodal, that is up to 5 or more than or less than more than 3 or less than 3 peaks, you'll be able to know that something is wrong with this histogram. So they are telling you that the normal one is trimodal. Okay, for RBC, it should be unimodal, 1 peak, the histogram. The platelet is also unimodal. All curves normally start and end at the baseline. Okay, all curves normally represent Gaussian distribution. Okay, x-axis cell size in femtoliter, y-axis the number of cells. Okay, we'll see that diagram now. Okay, so what we are saying is that the white blood cell graph histogram is trimodal. Okay, see 1 peak here, see it goes down, see another peak here. Okay, then see another peak here, all of them representing different population of cell. You can see this is for what? This is for what? Okay, red blood cell. It's unimodal. It starts from the base and ends at the base. So you'll be looking at for the characteristics of a normal histogram, okay, that you should have. And you can see it's unimodal, 1 peak. Okay, can see this is I think this is platelets. Okay, this is platelets. You can see starts from the peak, moves unimodal, goes down. Okay, so histogram as a quality control tool. So this histogram can be used to check what is really happening with the machine or with the patient sample. Okay, abnormality or indicators, probable cause, comments. So white blood cell histogram does not start at baseline. That may be as a result of giant platelets, nucleated red blood cells, or platelet clumping. They say review smear, correct for nucleated red blood cells. Okay, if elevation of left portion of granulocyte peak, the left portion is elevated, did not start at the base, the probable cause is as a result of left shift. You go and find out what left and right shift means when we are talking about especially the neutrophils. Okay, then review smear, elevation of ring portion of the granulocyte peak, elevation of the ring portion indicates neutropenia. So I think okay, RBC as a quality control. Okay, platelet as a quality control. What any abnormalities in the diagram can indicate. Those are what I think we'll see the diagram. Let's proceed further. We appreciate it further when we see the diagram. The other one you can read it up. So when you see the WBC clumping, what results are affected? What resolution may be attempted to obtain reliable results? If you see a WBC clumping, okay, may give you a first degree decrease in white blood cells. Okay. Okay. What resolution may be attempted to obtain reliable results? Redraw another EDTA specimen and review the results. collect citrates for CBC or CBC and platelets. Okay, you also collect in citrate tube if you see clump. Incubate blood 30 minutes and reanalyze. Estimate WBC from smear and perform manual differentiation. Perform a manual count to verify. Okay, append appropriate comments to the results. So this is how you try to resolve a situation of WBC clumping. So here, this is what I was trying to let you know when we get to the graph. So you can see this is an RBC histogram, which is supposed to be uh, unimodal. Okay, and now look at it here. It did not start from the baseline, number one, started from here, generating a bimodal peaks, 2 peaks. Okay, it's RBC. The normal one we say that is supposed to be unimodal, supposed to be like this, but that is not what it is. You can see the 2 peaks here. So what are some of the possible causes here? They said there'll be presence of giant platelets, microerythrocytes, fragmentocytes or dysplastic RBC, platelet clumps. These are the things that can cause the RBC histogram to have this bimodal look. Okay, so that's what I'm trying to say. And then this is RBC. You can see this place. It did not start and end down. Instead, it ended here. Curve not ending at baseline. Possible cause: cold agglutination, red blood cell agglutination, rouleau formation. I can also see this RBC. This is trying to, they're just analyzing the RBC graph, histogram. Okay, you can see this one forming how many modes peak. You can see this one here too. Okay, so multiple peak of RBC histogram. Possible cause: iron deficiency in recovery, infection or tumor anemia, visceral iron deficiency, red blood cell transfusions. So when you see an abnormality in any histogram of the cell, you try and find out what is causing it. Extreme leukocytosis. So this is a platelet which we were told should be also unimodal. And see, look at this one. It did not start from the baseline. The curve does not start at the baseline. Possible causes: high blank value, cell fragments, high numbers of bacteria, contaminated reagents, platelets aggregation. This is for platelet histogram. Okay, let me see if I have another platelet histogram. Multiple peak in platelets. Possible cause: platelet anisocytosis, recovery after chemotherapy, platelet aggregation. Okay. Oh, thank you. Oh, yeah. Have we seen white blood cell, red blood cell, platelets? Okay, good. Thank you. Any questions? Thank you. I'll try and unmute you now so that I can ask your questions.